Hi, good evening, everyone. So I'm Karishma, and thanks a lot for joining us here today. This is our 13th meetup and our very first online meetup, which is obviously due to the pandemic. Hope everyone's safe and healthy. So just to give you a little bit of context, we've been using the TechContainer platform to share knowledge on upcoming trends, and we hold sessions on various emerging technologies every month. Navis is a title sponsor for the event, and they provide solutions for port operations. Navis combines industry best practices with innovative technology to enable their container terminals and carriers alike to streamline their ocean supply chains and collaborate better together. Their N4 terminal operating system, TOS, powers the performance of more than 200 of the most advanced terminals in the world. And now moving on to the session plan for the day, to explain to us about the AI and ML behind COVID-19 spread pattern discovery, I take immense pleasure in introducing the speaker, Dr. Thendral. Our speaker, Dr. Thendral, is currently working at Kalasalingam Academy of Research and Education as an associate professor. He has 9 publications under his belt and is very skilled in big data analytics, optimization algorithms, data analysis, soft computing, and convolutional neural networks (CNN). So now I'll let the speaker take over. And just to add on one more thing, if you have any questions, please you can add it to the chat and we'll address it at the end of the session. Thank you.
Okay. Hello, everybody. I thank for the nice introduction given by Karishma. And is it audible for everybody? I hope.
You're audible, yeah. Go on.
Yeah. And I thank Mr. Parniraja for giving an opportunity for to let me have a study on this Aarogya Setu app, which is which is very trending now. So this session is about you can see the topic Aarogya Setu study. It's a study done by me on just by how it might be designed. So there is no document or anything about the design of this app. So we have just gone through this based on the location-based modeling. So I am going to give my idea about how this might be designed and how it can be enhanced. That's it. So we can directly take on. So first, my session will be divided into 2 things. First session will be kind of just a basic introduction, which is needed for the Aarogya Setu's app's design perspective, the algorithms which are related to that one. So we'll start with the basic algorithm which might be used there. About that, I will have some first discussion on that. Then we'll move on to the design perspective that I have studied upon. Okay. So myself, Thendral, I'm an associate professor. I think you all know. Okay. So machine learning is basically is divided into 2 categories. One is supervised machine learning. Other one is unsupervised learning. There are 2 main categories. There is one more category called semi-supervised, but that is not a main one. So it's a main thing is supervised and unsupervised. So if you see here in unsupervised category, there is a main thing. It's a clustering algorithm. So it's a clustering based algorithm. Supervised is a classification. This is the main thing in the supervised classification. Let me tell you what is supervised and what is unsupervised briefly. There are dimensional detection about the data, and the regression, which is for the continuous data. Classification is for the discrete data. It's there. It's a large area. Okay. So first, just I'll give a brief differentiating thing about supervised and unsupervised, and there is reinforcement learning is also there. Supervised learning is basically it's a training model. And it uses a data called label data. You see label data, and there is a direct feedback. It's for neural network, and it predicts the outcome. It's a prediction-based model. There is unsupervised learning. There are no labels. This is the main differentiator. The main differentiator is label data and label data. So this is a training-based. So we'll be training the model, and we will get a predicting one knowledge base which will predict the unknown data. So with the known data or a labeled data, we will train a model. Then once we give the unknown data, it will predict and gives the result back to us. Unsupervised learning is there are no labels for that data. I'll show the difference. What's the labeled data? What's unlabeled data is. Reinforcement learning is it's a high level. It's reward and punishment based learning. It is for kind of automatic car and then go game, chess game, those kind of thing. It's very complex algorithm involved here. Compared to supervised and unsupervised, reinforcement is very complex. It takes time to train. And so we are concentrating on supervised and unsupervised. Our aim will be in unsupervised here for the study of this app. So supervised, you see this differentiator. There is a orange colored ones and there's a blue colored ones. You see supervised, unsupervised, all are gray color. This is a data point. Each circle one is called a data point here. This is spatial representation. And there is a line which is demarcating this one. So this line is a classified line. So here, this is a classified data which is having a class value, blue class value, green, orange class value. This is unclassified data. Okay, so what's a class value? Let me show this example to you. Say, for example, this is a table we have. User ID, gender, age, salary, and finally there is a column purchased 0, 1, something, right? So this column, we will take it as a decision attribute. Attribute means column. So if it is having a decision, then we say it's a label data. Say, for example, pressure, temperature, humidity, wind direction, and finally wind speed is kept as a decision. The same way, if you are having a medical record, if you have a disease or not, then that yes or no disease, 0, 1%, that might be a class. Class means discrete value. Here, this is a discrete value. Purchase, this is a discrete value. That's why they say it's a classification. Here it's a regression because it's a continuous value, all floating by continuous values. So this decision, if there is a decision for the data, then we say it's a label data. So once we train a model, we'll just supply row by row, and then we just supply this decision also. Based on the decision, it will correct itself. It will go on learning. Then once this training is over, after the training got over, if I give unknown data, that means a data without this last column. That's unknown data. That then the trained model will predict the purchased this column value will predict. The same way, if I train with this whole data as a training set, then if I supply the unknown data or the data from the same training set, 1, 2, 3, 4 columns we have, then the 5th column value will be predicted. So classification is and regression, which are supervised, is a prediction-based model. And this is called label. The final column is called label column. But in case of, say, for example, the supervised learning, if you have a spam and non-spam mails, class is a spam or not spam. So once if I train my model with the data, spam or not spam, then the classifier will work once a mail comes, unknown data comes. This is a classifier, is a trained model. These three are unknown data. When the spam mail comes, this is trained to predict spam or not by having a training set already. It's trained already. So once the unknown set comes, it will just categorize. It's in this good mail, spam mail, likewise it will categorize. So it needs a label data. Unsupervised learning does not need a label data. See this one? So here all are unlabeled data, all uniform. So there are so many algorithms, clustering algorithms. So unsupervised, it's synonymous to clustering. So when you do unsupervised learning, we actually do clustering only. So this data is passed to K-means algorithm. This K-means algorithm just forms a cluster. So this is a cluster, orange one, green one, there's a purple one. 3 clusters are formed, and here there are 3 centroids. Each cluster will have a centroid. So now this is called a grouping of data. Unsupervised does not have a label. So we actually group the data. Nearness, which is near to each other, that is grouped together. This is a group of near data which is near to each other. So we will group the data. Then we'll just give a property to that. So this this is grouped together. So these are all same property. If we say it is having class A, then it can say it is class B, it is class C. So we can give a class after this grouping. So that is a main objective of unsupervised. Unsupervised means clustering. Supervised means classification. Unsupervised does not need a label data. That's the main differentiator. So as of now, that's enough. But one more thing I want to clarify here, because it's needed for the location-based data analysis. So here, if we got the temperature, you got pressure, relative humidity, and wind direction, and wind speed. So 1, 2, 3, 4. You have 4 columns, and the fifth column is also there. Okay, if we leave the fifth column, which is a class value, we have 4 columns. So this is called an attribute. Column is called attribute or a feature. Rows will call the instances or a tuples or a row database sense. Feature is a column. Okay, so rows, tuples, or instances we will be having. So this first data, which is having 4 values, it will be considered as a single point. Say, for example, here we are given a point here. This point is actually a 4-dimensional data. So we represent the data. We represent this data as a point in a spatial domain. So that is the main design behind lots and lots of algorithms of machine learning, which is all spatial based algorithms. So if you take one row is a point in a 4-dimensional space. So this is a 4-dimension: wind direction, humidity, pressure, temperature. Each one is a 1 dimension. So it's a point having 4 dimensions. So likewise, only we had to imagine. So this is how this unsupervised learning, the points are here. Okay. So there is one more classification. Now it is getting evolved. Unsupervised learning, supervised. Now there are deep learning comes, CNN comes, and lots of things are happening in the deep learning area. There's no data set available. It will generate the data sets. That's what deep learning's main objective. It will generate the data set to train. That is a current ML scenario nowadays. Okay. So here we are going to use one algorithm called the K nearest neighbor search algorithm for this study. So that's why I'm going to discuss only about this easiest algorithm of machine learning, which is called KNN, K nearest neighbor search algorithm. Basically, it's supervised algorithm. That means label data. It consists data spatial. Just now I told you, if you have 4 columns, each row is a 4-dimensional space points. That's what spatial points. Then uses distance measures to find similarity measure. So there is a similarity measure. If there are 2 points which are near to each other, that means they are similar to each other. If there are 2 points, that means each point means data set. Each point means 1 row in a data set. So if 2 rows are similar, means if 2 rows are similar, then the points are nearer to each other. So just imagine if you have 1 point over the other point, that means both are same points. So if the point is slightly moved from each other, then it is somewhat similar. If it is very far apart, 2 points are there. So very far apart means it is dissimilar. That's the way you have to analyze the data in spatial location. So if there is points are far, means it is not similar. It's highly dissimilar. So there are many measures for that. Famous measure is Euclidean measure. There's one more measure called Manhattan, which is a city block distance, Euclidean distance, cosine distance, and there are supremum distance. Many distances are available. Jaccard coefficients, many are available. So which is famous is Euclidean is very famous. It gives a promising results in many cases. So what's the Euclidean distance? We'll see, because it is used for finding distance between 2 points. So x1, y1, x2, y2, this is the points. These 2 are the points. Points means you have to imagine that data set which is present in the row in the data set. This is one row in the data set having only 2 columns. This point is a row in the data set having 2 columns, x2, y2. Now I want to find the distance between these 2 points. Sorry. Then we have to find this one. This is a point here having coefficients. Having dimension x2, y2. Then this is having x and y1. So this difference is y2 minus y1. This is y2 and this is y1. So this is y2 minus y1. This is x2 minus x1. So if you apply Pythagoras theorem, so hypotenuse is square of the sides. Then you can take a root of that. I'll get a distance. So this was the calculation here. So I know q1 minus p1, q2 minus p2. This one and this adjacent sides. So square of this one and summation will give us square of the distance. We take a root of this, then we'll be getting a distance. So this is Euclidean distance. Euclidean distance is sum of difference in squares taken roots. Okay. So for example, you are given 2 points. Difference is 3, difference is 4. So 4 square plus 3 square, taking roots. 5 is the distance. So there's a point here. Orange, this orange edge one side. This is one point here. There's a pink one and the purple one. So distance between these 2 is 5 based on Euclidean. Manhattan will not do a squaring and taking roots. It will directly find the difference. 5 minus 1, 4 minus 1, 7 it gives. Likewise, similarity measures are found out. If the distance is less, then it is more similar. That's what you have to just remember. If it is 0 means, then both points are actually same points. This less means more similar. Data is more similar. That's thing. So what is k nearest neighbor? So for example, this k nearest neighbor is very easy to explain. So this is unknown point here. The class star classes, that is a triangle classes. Now I want to find out where this yellow one, this new data will belong. Will it belong to star one or will it belong to triangular ones? So now we find the distance between this point to every other point based on Euclidean distance. This point, every other point we will find out. This is k is a numbers. How many neighbors, nearest neighbors you are analyzing? Here they are putting k equal to 3. So it will find the first 3 nearest neighbors of the point. Unknown data. This unknown data, that means which is in need of class value, whether it's a star class or it's a triangle class. So now the data point comes here. Now we find the distance between everybody else. Now this star is having one nearest. Out of these 3 nearest, one is a star, 2 are triangles. So then we apply polling. So the polling, if we count the polling, we see there are 2 triangles and 1 star. So we decide on triangle is the class for the unknown data. This is how it is actually decided. So you can imagine like this. This is k nearest neighbor. So if you are increasing the k value, so then you have to go for more number of nearest. If I put 10k, you have to find first 10 nearest neighbors. You have to find distance between every point to this point. Then you have to order it in ascending order. Then first 10 you have to select. In the first 10, which class is majority class? That's the value we give it to this one. So for example, you see this one. This is unknown data. If you put k equal to 3, this comes. These 3 are the nearest neighbors, 3 nearest neighbors. So here the 2 purple and 1 yellow. So based on k equal to 3, the unknown data will be given a purple value. But if you have a k equal to 6, we'll be having 4 yellow and 2 this one. So you'll give a yellow to this k equal to 6. So when the k differs and the decision differs. So k is actually a parameter which can be found out using other algorithms. The perfect k for this. That and all we can easily find out. So this is a k nearest neighbor classifier, which can be used in our study. And there is some basic concepts about clusters. So if you have clusters, there is a concept called centroid. Say this cluster, pink cluster, there's a green cluster. There is a centroid for this green cluster. There is a centroid for a yellow cluster. Likewise, we have centroid is a data point again. So these are data points. All these data points, when you apply clustering algorithm, we got say 4 clusters here. Each cluster centroid value. Centroid value is nothing but a summation of dimensions. So if you sum the dimensions, centroid point is calculated through taking mean of the corresponding dimensions of spatial data. So if you have 4-dimension data, take the mean of first dimension, then take the mean of second, then third, then fourth. Then that thing is nothing but a centroid. So if you see this one, this is all data. Then this point is a centroid data. So this is a cluster. Now if it is a 3-dimensional data, I will first calculate the mean of the first dimension of all the data, then the second dimension of all the data, then third dimension. Then that will be the dimension of centroid. So centroid is also a point. It is similar to, it is synonymous to center of circle. Circle is having a center, but clusters will have centroid because clusters are jarred. There is nothing like a round things, right? So it's like a jar, it's like a scattered things, but we say it's a cluster. So centroid means it is synonymous to center of a circle. It's like a center for a centroid. So dimensions average, you can easily find out. This is one more example for centroid, how the centroid looks like. Okay. Centroid calculation is the mean of dimensions. Then now we are moving on to the study. I'm putting a lot of emphasis on location-based modeling. So that's why I'm going for k nearest neighbor. There are other ways to go also that we'll discuss at the end of the study, alternative ways to study. Aarogya Setu app is very trending nowadays, and the government is insisting to install in containment zones. It's a must in containment zones, and it's downloaded a lot of number of times. Let us see what's the use for this. It protects yourself. It helps to protect yourself and the community. Precision tracking of the speed of spread of the COVID. It helps to find the spread, how the spread is happening, and it gives other advisories, health advisories, everything. These are all somewhat different. First, these two are the main important things. It helps you to protect yourself by giving risk value for you. It gives a risk value to you when you are moving around in the society. So when you're in the market or somewhere, it will give a risk value for you. How much risk you are in currently, wherever you are in, what's the risk of getting COVID. That's what news, and it is help for tracking the spread, but it is not for the public. It is for the government. Government can find the spread. That's what we'll learn today. How the spread is happening. These two are the main things. So Aarogya Setu, what is it? So it's a risk reduction model. And what's the features? What it uses? It uses location based. It needs a GPS. It's a must. All should be have the GPS on in that one. And it is Bluetooth based. Bluetooth should be on all the time. For if you install the app, both should be all on the time. All the time, integrated with the centralized medical database. Okay, so this app communicates with the medical database. This is not a very full-fledged medical database. Might be only related to COVID. They might have created just now only, because in India does not have a centralized medical database. There are a lot of laws for keeping the privacy. So, but this database might be related to only COVID, integrated with the Aadhaar database. So it is fully integrated with the Aadhaar database, and with your phone number. It's phone number is a major key here. With phone number, it does all the things. And the tracking, we can do tracking using this one, but not for individual, not for public. It can be used by the organization or a government. So this is what Aarogya Setu app is. What's the requirements? You need a GPS. GPS should always be enabled. Latitude longitude is found out. Bluetooth works in a short range, 5 meters range. It should also be always enabled. It is mainly used for giving risk value to you. If you are nearer to someone, it will communicate around the people through Bluetooth communication. Then it will give a risk value to you, whether you are contacting a person who is having a risk or not. He is highly risky people. You are just near to them or not. We'll just give. Bluetooth might be used only for that, but GPS is the main thing. Okay, so privacy concerns over the app now. So many are saying neurally based software freedom law center and the Internet Freedom Foundation, they are saying it is infringing on the privacy, lack of transparency in the app. They are saying there is a lack of transparency in the app mainly. We don't know what it is actually doing. You are saying something, but it will do something else. We can do anything once we give the access to all the things we have, and it is supplied and it is supported by the government too. So there are many concerns raised for this. But actually, what developers say, they are saying they have developed a randomized anonymous device ID that is used for all communication between app and the server. So if somebody tracks the data in between, whatever they have might not be useful. That's what they're saying. Data is deleted in 45 days from the non-risk users. So if they go on collecting data, say for example, if they collect data from me, latitude, longitude, position data, and if I'm for 45 days, if I'm not at all having any risk change, then they will delete the data. That's what they're saying. And 60 days from the date of discharge of a cure of a COVID patient, if somebody is having a disease confirmed, then the track, whatever they have tracked for that person, the data will be gone after 60 days. That's the policy they're having. That's what they say. Location data in which, in case you test positive, only to map places visited in past 14 days and for sanitization and testing to prevent further spread. They're saying if you are tested positive today, then they will track your movement or history, your location history for the last 14 days only for performing sanitization, and that's what they're saying. And they might catch others also who might be infected because of this person. So this is currently developers of the app says. But what is the reality? The app cannot work without GPS. That's fine. App does extensive analysis of GPS data. It will do. App needs and get all personal data of people associated through their mobile number. Mobile number is a key. The patient will give the mobile number. That is enough because mobile number is must for Aadhaar. So through that Aadhaar, you can get address and financial health, everything. You can get a lot more things. What are other mobiles he is owning? Everything you can get from Aadhaar. So mostly Aadhaar is linked to mobile, even though we don't know. Even though it is a code says it is not needed, but it's linked to mobile. PAN is already linked. PAN is linked to Aadhaar. So almost every bank is linked to PAN. Every bank will have phone number. So through that means everything will come into database. And banking and insurance, phone number is related to bank and insurance. From that they can lot of data. Ration card is linked to Aadhaar card, then mobile number. Then you can get the entire family details. Your family, who are the family members, how many members in the family, like this, anything they can get for you. Because if you are infected, then they will go for your family members. Then the passports, mobile Aadhaar is linked to passport, everything. Phone number is linked to passport. Then they get the foreign travel details, all your history, travel history they can get. Through that, they can find the people who traveled along with you. Likewise, they can do anything. So almost entire thing is, once you give the mobile number, government can get the whole data that is available to them. For effectiveness of app, all the above are actually needed. Without that, the app is meaningless. Okay, now we're going to analyze this. The following study provides a brief insight into the app, how the app might be designed based on location based. So it's about just study. We are just visualizing or finding or speculating that this might be the app's design, or it can be taken as a suggestion to enhance the efficacy of the app. So I identified 4 modules. One is a cluster identification, risk level prediction, decaying of risk levels, and tracking of neighborhood data. So 4 study is identified. 4 modules in this app I identified. So let me go through one by one. We'll start with cluster identification. So cluster identification, clustering is the main thing here. It's like I told you, unsupervised learning, but it is not a pure learning here. We're not going to use k-means kind of sort of things. It is like a k nearest neighbor search. Say there are a group of people, k number of people around an infected person or a high risk people, highly risk person, or you can say having COVID-19, or high risk can correspond to he might be having disease. So that's what high risk people, or somebody who's infected if that data is there. So you have to first find a group of person who are around that high risk people. K number of people might be around the person. So we have to find a cluster keeping that person as a centroid. That's why I explained the centroid. So if you take him as a centroid, one person is there, he is a high risk guy, or if he is infected, so we have to find a k number of people around that person. So how to find the k number? What is this number of persons k in a group is a parameter. It's a parameter that is under analysis, which is the best k. So if I want to find out 50 people around that person or 20 people around the person, k is equal to 20 or k is equal to 50, that itself is a study, which is the best parameter to go. That's a separate study. But just to listen to this, that there isn't k. K value is a number of people around that infected person. So cluster of that k number of people around the high risk person is found out through k nearest neighbor search. So let me say there is a person here, red. This person is infected or is a high risk guy. So now you are just finding 3NN search. 3NN search means you find only 3 nearest neighbors. Nearest neighbors means distance wise, Euclidean distance. That's why I explained Euclidean distance. So you have to find these many people are around that person, but you have to only find 3 people nearest to them. So that means you find distance between this red point to every blue point. Then you have to do ascending. Then which is the first 3 that you have to choose as 3. So the complexity is actually n. There are n people around that person. You have to find n distances. It's a big thing, because if there are 1,000 people around, you have to find 1,000 distances. Then you have to do ascending. Then you have to order. Then you have to get the k. That consumes a lot of time. So there are many algorithms for doing this also. So this is what PNN is finding 3 nearest people. So this is a cluster. We say this is a cluster, 3 people in a cluster. Now, for example, if you're going for 7 people in a cluster, threshold is 7. Okay. So for how to find that one, this is an infected person. Now I take one distance. Say for example, this is also again a parameter. One parameter that's again can be studied. So if you go for a 10 meters, so this is a person who's infected. His GPS location is known, latitude, longitude. Now from this GPS location, I put a 10 meters. Then we can put a circle around that 10 in the 10 meters radius around this latitude, longitude location. So we will get a full location name. So in this location, we can find out who are all the points present inside. So if you are able to identify 1, 2, 3, 4, 5 people which are present around this one, but our threshold is 7. If you have a threshold of 7, objective is you have to find a 7-sized cluster value. So we just increase the size one more. So 10 meters. So if I go every time 5 more adding. So if I go next time I'll go on for a 15. 15 wise I'll put a circle here. In that circle, how many new people are getting? So 4 more. So already 5 plus 4, 9. So 9 is exceeding our 7. So that means I stop it. So this is a stoppage criteria. So now 9 points are there, but our threshold is 7. So we might not get exactly 7 all the time. But what's the need of using this one? No need to find the distance between every point around that to the centroid. You just have to work only with the circle. Inside the circle, who are all there? There are algorithms for that. One way to find is there is an algorithm called KDT algorithm, which can be used to find nearest neighbors, which is used for finding nearest neighbors. So how it is found? See, these are all the points present in the neighborhood. These are the points present. We randomly choose one point. Now the objective is they want to find the nearest neighbor for 0.74. Okay, there is a point or a data which is having dimension 7 and 4. So these are all the points around that 74, not around that 74. There's a point lying in the spatial domain. Now they are choosing one value. Say for example, they are choosing x value. This is x value they are choosing. X value is 6. They choose x value 6. These are the points, but they choose a point which is having x value 6. This point is chosen. Then they just segregate all the points which are having less than x in the side, more than 6, more than x value, less than 6 in this side, more than 6 in the side. This is the tree dimension. So now we have 4 points in the right side. We have 5 points in the left side. See the x value? X value is less than 6. This x value is more than 6, 6, 7, 8, 7, 9. Then next level of the tree, they will use a y value. But here they are using x. Again, you can use x also, but they will go alternatively. So this what they first they are dividing by x. See this one? They are dividing the entire thing divided by x. So this line is drawn, vertical line. So there's a left side 1, 2, 3, 4, 5, and right side some points are 5 points are here. Fine. Now they are selecting y value. Y value is 4. So they will divide like this, horizontal. So first vertical, 2 things, then horizontal here for the red one. This is a red one. They're choosing this actually y actually. They're choosing 8. So y is 8. So out of these points, which are all having 8 or more than 8. See this one? 1, 2, 3 points are more than 8. Y value. It's not x value. Okay, sorry. This is having a y value less than 8. 2 and so that is why only 2 values are present less than 8. 3 values are present more than y here. We are doing a partition. This is a spatial partitions algorithms. So now in this left side the green, we are choosing 4. So 4 is a y value. Less than 4 y values points are here. These 2 points. Okay, 2, 3. 2, 3 is 2 is a x dimension. 3 is a y dimension. That's 2, 3 and 4, 1. The same way we're dividing. So once if you divide like that, our first question is 7, 4. 7, 4 is the point. This is the point we have. Around this point, we need to find out the nearest neighbor. So they will just find out the one full domain. So here, for example, they will select a full compartment, this blue compartment. So they just go to compartment 7, 4. They will start with this tree. 7, 4 is a 7 is a x. So 7 is more than 6. So go to the right side. Then y is greater than or equal to 8. Y value is 4. That means it goes to the left side. This blue. So this is the zone for this. So they will just give these 2 values. These 2 values, which is in the blue. That's a nearest neighbor for x. So this is a very elaborate algorithm, theory tree. So it's just I said, but you can just move up the tree and you can get the full zone. Zone wise you have to do. So once this tree is developed, I can just get the zone. This zone, blue zone is done. These two are nearest neighbors to this one. So there is it just reduces the complexity, time complexity for finding nearest neighbors. Theory tree algorithm. Likewise here we do. So now first point is we are doing clustering. So based on this, say for example, I'm taking 50% around a infected person or a high risk people, 50. So the cluster size is 50. There are 50 members in the cluster. Then we are going to, using this one, we will find out 50 members will be found out. Then next topic is risk level prediction. So the first of 50 members, we will be predicting what's the risk level, what's the risk value. And the risk value will be given as a green and or red fully 100%, or will give a scale shades from yellow to orange. So we are going to give a probability based risk level finding. So we're going to assess the risk level for everybody in the cluster. So for example, this is a cluster. There's a person here, and these four are, if you go for 4, 1, 2, 3, 4 in the cluster. First thing we will do is we will find the radius of the cluster. So this 4 members cluster is identified. Radius of the cluster we have to find out. What's the radius of the cluster? It's just radius of the cluster is average of distance between every point in the cluster to the centroid of the cluster. Centroid is the infected person's latitude, longitude, and these are the people who are around him. We know the GPS location of this guy. These 4 people's location we know. It's a 2D data. It's not a multidimensional Euclidean. It's just a 2D data, X and Y coordinates. Both are having, all the points are having X, Y coordinates only. So we apply Euclidean distance. We find the distance between the centroid to every other point. Black one, blue one, yellow one, red one. We find the distance. We sum it up, all these distances. Then we take an average by 4 we do. Then that is called a radius of the cluster. So if the people are very nearer to each other, people are nearer to this infected person, means the radius of the circle or radius of the cluster will be low. If there are very far apart, there are people who are there, 4 people are there, but the 4 people can be far apart. But if the guy goes to a market, the 4 people will be very nearer to that guy. So the radius of the cluster will be reduced. But if he walks in a street which is empty, then if you want to find out who is the nearest 4, that they may be far apart from that person, then radius will be very large. So if he is in a crowded place, the radius is less. That's what find out. But first we are going to find only the 4 members. Then we find the radius of the cluster. That is found out. The radius is mentioned as R. So here the problem I told you, this is probability based risk assessment model. We're going to give a value of risk probability value to this one. This is a formula I'm a formulator. The radius of the cluster is found out, and the distance between point I in the cluster. Point I means person, every person in the cluster, to the infected person. Infected person is centroid. That is termed as D. D is the distance between a person in the cluster to the infected person. That is this D. This R is the radius of the cluster that infected guy is currently in. So we are finding a ratio of D to R. So if D is very low in that radius, that means this second term will be very less. That means 1 minus will be more. Then I can take a log of this one, that will be more. So if the D is very less, this ratio will be less. Then 1 minus will give a more value, log will give a more value, PA will get a more value. So probability of getting infection if it's nearer to that person. D is actually, this is D. You have to understand, this is D. The summation and taking average is radius. This is D. So this D by radius for this person. So based on this, we are finding a probability. This the reason for giving D by R ratio is to take into account the density of the people. So if the radius is very less and the people will be very near to each other, then probability of getting is more. Asymptotic infection can be more. So that is why we are going for D by R. Otherwise, we can just go with a D. If it's nearer to that one, then we can just give a more PA value. Why we are introducing R? That's what the introduction of R is. If the density of the people in the density, if more means cluster size is low. So we are taking into account the density of the people or cluster size. That's why this R is introduced. Otherwise, there is no need for R. That's the distance is low means I can give a bigger p-value, probability value. So this one way. One more alternate is there, which is a common function. We are using Gaussian function. The Gaussian function can be applied to find the probability. This is the probability. So R is the radius here. So the radius means here radius means sorry, this R is not a radius, it's a distance. Actually, it should be D. So when the distance increases, then we can say, see, this is a Gaussian. Gaussian is a bell curve. Bell curve is, this is a distance. If the distance increases in this x-axis, the y-axis decreases. This is a bell value. So this eta is about the bell width. See, 0.1 bell width. The red one with this purple one with the green one with. But all are reducing. If the x-axis increases, y decreases. So this is an inverse function. So Gaussian is a very prominent function used in many places where it's a radial basis kind of operation where the difference is there. So this distance is more distance from the current person. If you want to leave out a radius, if you want to leave out the radius of the cluster, just the distance alone we can take into account. We can use the distance is low means probability is high. We can give. So probability based algorithm. So probability is actually probability ranges from 0 to 1. So every person in that cluster will have a assessment done. So if a person is nearer, his probability of getting infection is more. The person is far apart, this probability is less because the d value is more. If the d value is more, this is more. This will be less, log will be less. So if the person is far from the infected person, they're giving least probability of chance of getting infection. So there's no chance of getting infection. It's a probable carrier. We are not confirming anything. Likewise, it's just getting coloring. It's all based on coloring. We give color. So in the shades, you will give from yellow to orange. So color 1 will give for this guy, value 1 for this guy, value 5 for this one, value 3 for this one. Likewise, we can give based on nearness. So there's a second one. We are giving assessing this value. Overlapping clusters. So sometimes there are two persons infected or high risk guy. This is a high risk guy. This cluster is 4. This cluster is nearer. Okay. This guy's cluster is also 4. 1, 2, 3, 4 here. But the cluster radius is very far. Okay, because the people is in a different area, latitude, longitude. So now these three are influenced by only this person. But this person is influenced by this infected person and this person also. So the probability will be coming from this one also and from this one too. There are two probabilities calculated. So these two probabilities are needed. So probability of A and B, if you perform that one, you have to do a multiplication of both probabilities. So that's what here. So each probability is Pi. If there are 1 to n, n being number of infected or high risk people influencing the point I. So here there are two people, two infected people are influencing this one. So P calculated through this should be multiplied together to get a total cumulative value. So if two bigger values are multiplied, I'll be getting a bigger value. If two smaller values are multiplied, it will go further down. So it's all fractions. So probability is cumulative probability will be coming. So this one more. So there are many people around. You will be influenced by everybody. So it's all just purely location based. No more parameters are added to this. So once this is cumulative calculation is done, now risk level decay. There is one more. This is a third module, which is a decay. There is a parameter called decay parameter. So after 14 days, the value of probability will start to reduce. So after the 14th day, if no change occurs, it will start to reduce. How it is going to reduce? So this is eta is an incremental number of days after 14th day. So e power minus eta number of days, and this becomes width. So again, we are using a Gaussian. So if eta increases, if number of days goes on increasing, then this whole term will decrease. If this decreases, then it will getting a smaller chunk of this. You are finding a new value. New value will be reduced value. So this is if days increases, then new value will decrease because this will be decreasing. This is decreasing means this is a fraction. In the fraction, you are getting a small chunk. The new will be decreased. So decay will go on reducing, but if you see the bell curve will never reach zero. It will go towards zero. So if it, we can just write one function saying that. So if it's going, if nu is going below threshold value, then put zero after some days. After 14th day, it will start to reduce. That's what. Okay. Then fourth is tracking of neighborhood data. So if a colored person turns positive for COVID, database is updated by hospital. This is what tracking now. So now coloring is done. As of now, we have done coloring, decay, everything is fine. Then tracking of neighborhood data, how the people are getting tracked, what to do, what they're planning to do. If a colored person, that means in the orange zone, so he is not, he is actually turned, say for example, this is the person infected, or he is above a threshold. If he is above a threshold, we can say it is kind of infected. These are our implementation details. Okay. If these four will be marked by this person, colored. These four will be colored by this person. So that is what the assessments they are doing. Okay. If an assessment person gets some sickness and he goes to hospital, and if he found to be having the disease, if he is positive for the COVID, then what happens? The hospital will update the database. His mobile number is turned positive, confirmed cases. So if that person is turned positive, then database is updated by the hospital, then mobile number will be updated. Then the person's location history table map with the risk values analyzed. Now we are going to backtrack. Now we're going to analyze the his history, travel history. Travel history means we can say movement history, where and all he has gone in the previous days. So once he turns positive, we'll be start tracking. Largest jump in risk. So how we can track? This is one way. There are many ways to do. One way is, so for example, the guy has been found positive. This is a day-wise risk. P1 is the first day, second day, third day, to sixth day. Sixth day, say for example, he is found to be positive. Every day's latitude, longitude, we are just maintaining. It can be average. These are all implementation things. It can be average. The probability can be average, because how long you will update. Every 1 hour you can update the probability, or that all other parameters. Okay, so it can be average. So for example, this is a sixth day's probability. Probability means risk value, the color value, and the sixth day's location we have, where is averagely moving around. Then we'll find the difference. Previous day's difference is a delta value. We find the delta. So delta is a P6 minus P5, or a difference, you can say, not a minus, difference between 2 days. This is a probability difference. We find the probability difference for the person. This is an infected person. The person is turned positive. When we are going to track, if a colored person turns positive, then only we do this. So if he turns positive, we find the difference of probabilities of that person for the previous days. We can go up to 1 month, 2 months, 3 months, or not, up to 1 month you can say, because in 1 month it will show the symptom, maximum 1 month. So in 1 month, every day between 2 days, consecutive days, we find the difference. Whenever there is a largest jump, the third point, if you see, there is a largest jump in risk probability difference. That is taken as a reference point to start the tracking. That's what, say for example, P3 minus P2 is the largest difference. P2 was very low, but P3 was very high. That means he might have come around many people who is having high risk. Then P3 is very large and P2 is small. So this, out of all these differences, this P3 minus P2 is so high. That means from this day onwards, the third day onwards, where and all he has moved. So this is a place, latitude, longitude on the third day. So we know the neighborhood at this latitude, longitude, who are all the person around that one. We know already, because we have a database of cluster formation. So where and all he is, this latitude, longitude, in which clusters it belongs to. Then this one, which belongs to which clusters. We identify all the clusters of these points. Then the cluster members we can find out. In that cluster members, we can find the color analysis. We can order them. Then we can go for them. So we can go and track them, or we can find who are all they have contacted. Likewise, you can find out, or their family members from the ration card things, we can find out their family members. So this is an infected person. His jump is very high in here. From this latitude longitude we can get. From this point onwards, we can find out, we can track all the clusters he was in. Then the cluster members can be identified. Their family members can be identified. All can be tracked. So this gives an insight into tracking. So this is one way to do. There are many other ways to do. So this tracking, this way of tracking. Now, what is the main challenges? What are the challenges here? Fixing high-risk persons to start with. Who's high-risk guy? So we have to set a threshold. If people are getting orange, yellow to orange, they're going on increasing in the assessment value. So once if we keep 80%, say if it's above 3/4, 3/4 is a probability value. If it is above 3/4, we are going to consider that guy as if he is positive. He is not. He might not have gone to hospital to check, but he is already coming in contact with many people, and his coloring is getting thicker and thicker. So we can just say he is a high-risk guy, or he is kind of a positive person without even testing. We can just say he is positive. It's an assumption. Okay. So how to fix this one? This is one of the challenge. There's a parameter involved. This will affect our predicaments. Frequency of cluster formation. So one guy is say at this time, one guy is present here. We find 50 people around him. After half an hour, we find 50 people around him. Next half an hour. So likewise, we are going. What is the time frame? Every half an hour are we going to find, or every 10 minutes are we going to track people? So it's a huge calculation. How many people are there? Many people are there. We are finding 50 people for everybody for every 5 minutes. We are finding. So it's a bigger calculation. What is the frequency of cluster formation and the risk value assessments? This parameter is also highly in question. We have to do optimization here. Fixing number of members for clusters. How many members? So for example, if a person is infected, I want to find 50 or 20 or 100 people around them. How to find that one? That number is also a parameter we have to question, and we have to find it's only a priori. By doing a lot of trial and error only, we can come at a probable number. So it's all randomization, heuristics involved, assumptions involved, hypothesis involved. So all things will come into picture. Threshold for difference in probabilities. What's the threshold here? We are finding difference, delta value. What is the exact difference? Or after, what is the threshold value, so that if it crosses, I can start tracking from that day onwards. So if I start tracking from this day effective, or if I start tracking from this day which is effective, because there might be people who are infected in this area. He might not have infected anybody in this one. He might have infected some people here, but we started tracking from this place alone. So these are all the many things which are involved, but obviously machine learning algorithms or this kind of computational intelligence all have a flaw. They have error rates. So these are some challenges involved. And one more constraint in going via this kind of GPS-based location is this cannot be applied for a very large multi-story building. Say, for example, if there is a skyscraper with 80 floors, 90 floors. So in that skyscraper, people will have same latitude, longitude. So in the different floors. So it is not good for GPS. Will work in open space, it is fine. But if it is in a high skyscraper where there are a lot of people around in the same time, so how it spread inside that building, it is tough to find out. So GPS has a constraint. It works only in outdoors. In indoors, we need an indoor positioning system. So we have to integrate GPS along with indoor positioning system. That's also one more area. Technologies that can be applied to optimize parallel processing. So cluster formation is independent of each other. So I'm forming lots and lots of clusters, but the location is different. So we can apply a heavy parallel processing to find out clusters. And we can do a map reduce. What's map reduce? I think people might know. It's a big data summarization of results. Parallel processing is different. It will parallel process, but cluster computing will do. It will parallel process, but this map reduce will integrate the results. So here, where we are applying this, so this might be given to one thread. It will come up with one probability. This will come up with a probability. Multiplication is reduction. So mapping. So the same person, this is the same person is mapped to this person and this person. So this probability will be reduced. So mapping and reduction for cumulative risk prediction. For that we can do a map reduce. Then a lot of randomization optimization algorithms will come into picture for optimizing the various parameters. We have identified only some parameters are identified here. There are many new parameters will come into picture once we start going deep analysis. So there's a technologies can be mapped. We can use big data algorithms. We have used parallel computing algorithms. We can use all optimization algorithms to enhance the app. Some features to upgrade. So risk value assessment. Now we are doing the risk value assessment just based on the location or the distance, distance and the radius, only the location based. But we can analyze based on travel history. So if a person is nearer to a high risk person, but we can include his travel history also. So for example, this person is here. This person is here around this person is infected. We are going to assess the risk for this person. So we are just not only using this distance, we can use the age also, age of this person. He might have just come from a risky foreign country where there was a high number of infections. So that can be taken into account. His previous ailments, if you have medical records for this, he is a heart patient, or he is having diabetes, or he is having some other ailments which can be taken into account. So we can apply those kind of other parameters to decide the probability value or to come to the risk value assessments. You can take ailments. He is from containment zone. Okay, the one we are updating, he might be from containment zone. For him, we will give us some extra values to that because he is again going to the containment area. So we will increase the risk value. Containment zone, we can get the address. The address might be already contained. So we know from latitude, longitude, we know which area is contained. This person's average movement, if it is his address might be different, but his residing might be different. So for the last 1 month, we can find out his movement. If he is in the containment zone, apart from the distance, we will just give extra probability values because he is from containment zone. He might be having ailments. If he is very aged person, we will give more so that he will become red quickly, so that he can be able to, government can go and track him, or he can be contacted by some health monitors. So high risk people, but not tested positive. So risk value can be given by high risk people also. So if some people are going towards red, but they are not getting tested, so they can also be included for getting updated. Say for example, this guy is turned into finally red, so he can act like an infected person. So for updating this person, I can use these both persons value to update this person. So if he crosses a certain threshold value, even though he didn't go to hospital and check for this one, but if he crosses a certain threshold, now he is also considered as infected. Now this persons will be updated by these three people. So that's what this point is about. So high risk people but not tested positive can also be used for risk assessment. This can be achieved through regression. So all these things can be achieved through regression analysis. Okay, some more features. Priority-based tracking of persons and sanitation can be done. So now we have colored people. So if you're having highly colored, he is moving towards red, we can prioritize them. Then we can map the risk level. If you have a risk level along with the daily acquittance, say for example, one guy is in 80% value of risk value, and his acquittance is very low. He is meeting daily 10 people. He is around only 10 people. But there is a guy with only 60% or 65%, but he is meeting around 200 people daily. So the risk level can be mapped with acquittance. So even though the 80% guy is meeting only 10 people, but the 65 is meeting more number of people. So we can just find a ratio between risk level to acquittance ratio that can be used to prioritize whom to go for, whom we have to track. Whether to track a guy with 80% or to track a guy with 70%. But 80% is meeting very less number of people, 70 is meeting a lot of people. So that ratio will help us to prioritize whom to go for, whom to go after. So that's priority-based tracking. These are some more features we can upgrade on that one. So this analysis has been done. So if you have any questions, You can ask me.
So before we open the floor for questions, I'd like to thank the speaker for putting all this time and effort in this session. I'm sure all of us learned a lot about the various machine learning algorithms and its relevance to the current scenario. Thank you, Thendral. Thanks a lot. And everyone who joined us today, thanks a lot. I really hope you found it informative and interesting as well. And now, if you still have any questions, feel free to ask the speaker. You can have a one-on-one with him. And I think we did have one question already from someone who asked how nearby neighbors who did not install the apps are identified. You can address that.
Yeah. So it's a must to install the app. Without the app, now nobody can be tracked. So here, how many neighbors who did not install the app are identified? No. So if we did not install the app, then somebody might be infected and he is near to you, you will not know. So that's a constraint. That is why government is insisting people who are in the containment zone to install. That's a must for them. So if an infected person without app is very risky. So people will go near him, nobody will know about whether he's having or not. He should also have the app installed. Because the Bluetooth will be having a nearby contacts.
If you have any more questions, you can add it to the chat. It will be addressed. Someone's asked how long app can maintain the data.
Okay. So that's so here. So the government has said, or the developers who have done this one, they have said 45 days for a person. Say I got the app, I got some risk already assessed for me. Say for example, I came into 60%, but after that it will start reducing. So after 45 days, non-risk users, I might have come into risky area. They might have been following me. If my risk level crossed 60, I might not know. If the risk level crossed 60, they might be following. But after 45 days, if the risk level is all the time on the 60 for 45 days continuously, they will delete the data. This is what the government says. And one more thing is, if the person is positive, 60 days from date of discharge, they will go on tracking where he is moving. So he is discharged. He's got positive. He got treatments. He is discharged. For 60 days, they will track him. He has to install the app. They will track him. So after 60 days, they will delete his data. That's what the app follows. But we don't know what exactly is internally happening. So this is what they say. There is always a disclaimer. People used to sign without reading. So in case we test positive, only to map places visited in first 14 days. So if you are tested positive for the 14 days previous, this is for next 60 days, they will track you. After that, they will delete the data. This is once I test positive, they will go for the history, previous 14 days, and they go for sanitization of the places where and all I visited for the previous 14 days. So before 14 days, after 60 days, if I'm positive, 45 days, if I'm very prone to disease. That's what the app says.
Okay, Suresh, I hope your question was addressed. And we have another question from Jay. He's asked, what are the technologies that are used in the app?
So that's what we have discussed. Clustering algorithms are used, and tracking based normal algorithms, normal mathematical algorithms, plus unsupervised clustering algorithms. And if you include more parameters, as I told in the last slides, they include age and the previous visits. We can go for regression. Regression is a supervised machine learning algorithms. So it's like a mathematical algorithms, like concrete math, along with machine learning, which is a soft math. Both can be used. That's what we have discussed. And lastly, I told you big data for MapReduce. Through MapReduce, we can easily arrive at the cumulative probability. We can go for a cluster computing, or we can go, that's what parallel computing. Those algorithms will come into picture. MapReduce algorithms, cluster computing algorithms will come into picture. So many are involved.
I don't see any more questions. If you still have any, add it. And okay, I think okay. Someone's asked, day by day the COVID-19 spread rate is increasing. Only alternate solution for this.
That is expert should answer that. Very big expert.
Okay, I think yeah, those are the only questions we got. So thanks a lot, everyone. So if we don't have any more questions, we can end the session here. Thank you.
Thanks for listening. Thanks for listening.